Yeah.
I do.
Okay, I feel better now.
We have one more common exam and then we have the final.
Thank you for clearing that up.
Yeah, you just make me about one.
1, 2.
Two more tests?
Yes, 2 more tests.
What do you think about?
So yeah, the multiple choice one.
Wow.
I remember.
I thought they were 4.
You were fine. Yeah.
I missed one of the multiple choices. I was on my way home and I was like, oh, I'm an idiot. Oh. It was a stupid one. It was like the trick and the this and that. I just went through too fast. You're like, oh, no, they're wrong. Right, when they're at a constant speed.
But when they're at a constant speed, it's equal.
I got one of those right now. Driving home and I was like, oh. Dang it, that was such an easy question. No, I got that. I'm pretty sure I got that.
I mean, it depends. I don't like the acceleration of the car.
Remind me of the question.
You said a truck and a car are coming, and which one has a greater force on the other?
And I
didn't say.
So I said, I forget what I said, but then I wrote a note. Well, it depends on the velocity of the car. It could be more straight.
I assume
Remember Newton's third law. Remember Newton's third law.
But not.
Are they not accelerating towards each other?
Doesn't matter.
I kept trying to get out of the car when they got
Yeah,
You're talking about the forces, the force of the car on the truck and the force of the truck on the car. Newton's third law, by Newton's third law, they're equal and opposite. Doesn't matter whether they're accelerating or not.
You wanted to get out.
Doesn't matter.
Yeah, I'm good. I just went by instinct on that.
Yeah,
And I slept. When she said
That's some sleep.
slammed myself against the wall and just started sliding.
I'm going to work on it.
Do you have any more classes?
Yeah.
Just keep focused. It's Friday. Light at the end of the
When I was there,
Yeah.
I moved to a lot to the left.
But they're going to be like, everybody's so used to me.
Okay, so let's start. We have 2 exams remaining. One is a regular chapter level test, which will be on Thursday evening, November 21st.
Don't let him in.
We went outside today.
Anybody after you?
I thought. Oh, yeah.
Okay, so the November 21st, Thursday evening, will be the next chapter exam, 1 through 7. So chapters 6 and 7 will be included on that. And chapter 7 is pretty lengthy. It's the one we're just starting now. There's a lot to chapter 7. And the next exam will not be a regular chapter test. It'll be the comprehensive final, which will include chapters 8 and 10. Chapter 9 is not very much. Well, I shouldn't say that. Chapter 9 is very interesting. We won't spend a lot of time on it, and there won't be really any of Chapter 9 appearing on the test. Okay. Chapter 9 is an overview of the things required to get a manned mission to Mars, and it kind of combines a lot of the stuff that we've done, especially after Chapter 8. We'll consider orbital mechanics and stuff. So it's kind of neat to see how all of it ties together, and the theme comes back in the second volume, the E&M textbook as well. So it's kind of neat to see, but it won't be on the final. But Chapter 10, I'm still hoping that we will get to do at least 3 classes on special relativity at the end, and that will be on the final. Okay, no office hours after class today. I have a dentist appointment, so if anybody expecting to come by, I was figuring maybe after the exam I wouldn't see anybody in my office today. So, tell you a little story.
Dr. Don, could I ask
Yes,
you a
ma'am.
question about the final?
Sure.
I know some classes have like the replacement policy. I was just wondering if you're just like the final, it replaces your lowest test grade, but it counts
No.
Yeah,
It's pretty straightforward. It's spelled out in the syllabus. The final counts some percentage. What is it, 30%, something like that? I can't remember. Of the grade, it's deliberately graded so that the last exam is very weighted. Yes, sir.
You need to see my Halloween costume.
No, I didn't.
No. You didn't want to see it.
It was amazing. I
Okay.
had everything. I had everything labeled out. I even did research on it.
I'm sorry I missed it.
Research on it.
Okay. So let me tell you a little story. So I majored in physics at University of Florida. Gainesville. I was a transfer student, so I did 2 years at the JC in Jacksonville and then moved to Florida. And when I started off as a freshman in physics, actually I wasn't in physics yet, I thought I was an engineer because I didn't know you could major in physics. I mean, I thought it was cool stuff, but I had no idea you could major in stuff. And then when I got to college, I found out. And so then I became a physics major, right, because that was what I knew I wanted to do that. And so really enjoyed the physics classes. You know, I was good at turning the crank, right? You know, good at that. Okay, you should stick with this. You're good at this. Turn the crank. Freshman physics was a bit perplexing. There was some stuff I didn't understand. It sounded like a circular argument. Didn't quite make a lot of sense, but I could solve the problems. And so I figured I would get to, at some level, the better stuff, higher level stuff. It'll click. Somebody will explain it all, right? It'll all make sense. And so I kept going to more advanced classes and stuff. And I went to Caltech, and which is a really small school. There's 1,000 undergraduates and 1,000 grad students, so it's a tiny little place. And so taking classes there and stuff. But you walk in the first day of class, it was orientation for graduate students. Welcome to the Marine Corps. That's the way they introduce themselves. That's the way they think of themselves. The Marine Corps Physics Departments. And so they just open the fire hydrant and you're supposed to swallow somehow. You know, this stuff just comes at you. It was just really intense couple of years. Then I went to a class, you know, let's see. Do you know this guy?
Oh.
So he was on the faculty there, and we're spread around. He's teaching a class in quantum field theory. And so, okay, got to go see that. So I registered for that class. There were about 5 of us in the front row. Of course, they had to reserve the auditorium because it was just packed. You know, there were hundreds of people in the room, standing room only in the back. You know, and 5 of us are in the class, taking this class, and I'm sitting down in the front row. The 5 of us are kind of, what have we gotten into here? And so Feynman is, if you've ever seen any of his lectures, they're wonderful stuff. They're very animated. He's very articulate. He slips in and out of this Brooklyn accent, kind of depending on what he wants.
Brooklyn?
Yeah, whatever he wants, he's in the mood for. So you're sitting there listening to the lectures. They're fantastic lectures. You know, while he's lecturing, everything, it just seems like the universe is just unfolding for you. And then you go home and you try to work a homework problem, and it just kind of evaporates. You know, it's not there anymore. It just disappears.
Sounds like this.
So, oh, it's much more than that. So he assigned one homework problem for that class, the first day, and that was it. He said, you have to make up your own homework problems. And I'll assign the first one. The rest of them you make up and turn them in, and he graded them. So that was an interesting experience, you know, because he felt that just figuring out what was an interesting question was most of the learning, you know, and then trying to answer what was an answerable question too, right? What could be answered, what can't be answered, just trying to frame a question. So he would take these homeworks, and you know, I start turning in homeworks, and he would red pen all over, you know, and but he was very encouraging. Yeah, it looks interesting. You should keep working on this. So you know, next time I keep on going and stuff like that. Found out later he liked to take the homework when he was ready to grade the stack of homework from the 5 of us. He would go to the strip bar in Pasadena, and he would grade them, and I didn't know that at the time. He'd hand them back. He went to a strip club. Now, I don't know how he could concentrate on grading, but he Anyway,
How'd you know that?
he told me.
It's a wide number, so.
How did that come out? Like, yeah, so your grade, yeah, it wasn't good. It wasn't good.
Grading it in a quiet environment was too easy. I think.
It was more challenging,
I need
I
a
guess.
distraction.
Need a distraction. Anyway, so I got up to Gumption. I said, "Would you be my advisor?" And he said. So he went back, looked at the homework. He said, "Yeah, okay." He said, "I'll do that." But he said, "I'm a terrible advisor." He said, "Because I can't assign you a thesis problem. Because if I'm interested in it, if it's something that I'm interested in, and I give it to you, I'll get impatient because it'll take you a long time to solve it. And I'll get impatient. I'll go home one weekend and solve it. And then where will you be, right? You're going to be stuck." He said, "So you have to come up with your own problem." And he said, "Which is really tough because if it's uninteresting to him, I won't be of much help to you. And if it's interesting, I might go home." So he said, "I'm a terrible advisor that way." He said, "But we could try it." So, okay. So I got to come up with my own problems again. I mean, it's the same pattern again. It's like the homework for the test. You got to come up with your own stuff. So I never did really come up with a big problem. I just came up with a lot of little problems, and I would go into his office, can we spend a few minutes? And he would be standing in front of that blackboard there, and there was all kinds of stuff over the blackboard. He had stuff written up in the corner and stuff. I mean, it was, half the time I just wanted to see what he was doing, and just spend time what you're working on. And so then he'd erase some little corner down here and say, "Okay, show me what you're doing." And I'd show him a little calculation. He'd ask a few questions, and I'd try to explain what I was doing, and after a while he'd kind of figure out what was going on. Oh, okay, that's good. So like the tau had just been discovered. This is a really small problem. The tau had just been discovered, which is the electron. So there's the mu, and then there's the tau, third in the series, more massive. And so it had just been discovered, and so I was trying to calculate the branching ratios for all the different decay processes. Real straightforward, simple calculation for me in terms of his textbook stuff. But for him, I didn't realize at the time he's the one who worked out all the stuff that was in the textbooks, right? I didn't even understand that. So he kept asking questions about, well, why'd you do it like that? Meaning, of course, I just looked it up in the textbook. That's the way it's supposed to be, and I didn't realize it didn't have to be that way, right? Anyway, it was wonderful to go in there and spend like an hour or two talking with him about stuff, and he would make suggestions and stuff like that. So it was fantastic, and he was very grandfatherly towards graduate students for the most part. He was just encouraging, yeah, that's really good. Except I saw on one or two occasions when he thought somebody was getting a little full of himself, and he really knew how to bring somebody down pretty quick. Sometimes it would be in public, and that was pretty embarrassing. Right? So he liked it when you just talk to him, simple, straightforward, just talk, right? And he was happy with any kinds of questions. He liked all kinds of stuff. Everything was fair game to him. Everything was interesting. So any kinds of questions would be interesting to him. One day he came in. He was a runner. Used to go jogging, and one day he came in, and the side of his face was all bloody, and scabbed over and stuff, or partly scabbed over. He had a big bandage on it and stuff. He had fallen running, and so they took him to the hospital later, and they found out he had cancer. It was very well developed in his intestines, and so he stopped coming. And his postdoc at the time told me, "It doesn't look good. It's really, you're going to have to operate, and it looks like it may be a long time before if he does recover." So at that point, I was kind of figuring out what I was going to do, and eventually I knew about this group that was in solid state area, and I actually switched over to solid state. So I finished up with that other group. But he did recover after I graduated. I think I was his last graduate student. At least I didn't finish with him, so somebody else was the last graduate student. But anyway, he then, remember the shuttle that blew up? He was on the investigation committee that investigated this, and I don't know if you've ever seen any of the videos from that, but they had these O-rings that got cold and apparently didn't deform in the right way to relieve stresses because they got stiff and because they were cold. And that was part of the problem. Part of what happened was there's a leak through a joint that was supposed to be closed by the O-ring, and the flames went out and blew up, ignited the fuel tank. So he did the very simple test of just putting one of these O-rings in the water, ice water that they had on this desk. You know, they had this big commission and having a public hearing with the reporters and stuff to talk about their findings, and Feynman just sticks an O-ring in the ice water and waits until the right moment, and then he pulls out this O-ring and it's all stiff, and he demonstrates how it doesn't bend and stuff, and that captured a lot of attention. A simple demonstration. So he was always very firmly convinced, though, and this is something that I think everybody really needs to listen to with regards to this. If you can't explain it in simple terms, remember this quote I had from him, if you can't explain it in simple terms, then you really don't understand it. And I would ask him sometimes, well, why is it, for example, I asked him this, that spin 1/2 particles behave like fermions and spin integer spin particles behave like bosons? You'll learn about this. And he said, I don't really understand. He said, I can give you some sophisticated theory, and I can explain it in terms of those kinds of arguments, but I don't really understand it myself. I've tried, and that was it. Right? So there were a lot of things that he was still fiddling with, stuff that would appear on the blackboard up there. He would fiddle with. So I think just the stuff that he had in his notebooks and on the blackboards and stuff must have been fantastic to deal with. Anyway, so a little story to encourage you to work hard. There are a lot of opportunities out there in physics to meet people, and okay, so, but today we're dealing with rigid body motion. And specifically with regards to rigid body motion, we're going to focus right now on a little piece of a rigid body, which is the piece is moving. Remember, what characterizes rigid body rotation? If we have some kind of, we like to draw potatoes when we're doing rigid bodies for some reason. And we have this thing that's spinning around an axis, and we indicate the rate of spin. So this, we construct with this a vector whose direction is the axis of rotation and whose magnitude is the rate of rotation, where the period of rotation is 2 pi over omega. It's called the angular velocity vector. Well, angular velocity is omega, and the angular velocity vector is omega vector. And that's shared by every piece of that rigid body while it spins. Every piece of the rigid body is executing what kind of motion? So let's label a little piece here, and that little piece is doing what kind of motion? Spinning. Yeah. We're going to call that uniform circular motion. Another one, UCM. UCM. Uniform circular motion. So it's circular, meaning that the distance from the origin is fixed. Let's put it this way: R equals R is constant. The distance from the origin is constant. That makes it circular, and uniform in the sense that the velocity or speed, the magnitude of the velocity, that is the speed, is also a constant. That's what makes it uniform. And this omega is the relationship between the speed and the radius that we obtained last time. Right? The speed is proportional to the radius and this angular velocity, omega. Okay. So now let's investigate this question here. I'm going to make use of a theorem. You're going to prove a theorem in the homework. We're going to do two of them. I'm going to do one for you, and you're going to do the second one in homework. Let's take the derivative of a dot product and a cross product with respect to time, so that A and B are both time-dependent vectors. They change possibly with time. So we're going to do this here in class. That the time derivative of a dot product between two vectors can be written like that. And the time derivative of a cross product is similar. So you're going to prove the second one. We're going to do the first one here in class right now because I'm going to make use of it. So how about that? How could we go about proving, say, the first one?
You could say
What do you think?
change A dot B to AB cos theta.
Okay. Right. And that would get us then, we'd have, if we use the fundamental form, this is the fundamental form of the dot product, and that's, I'm glad that you start thinking about it in those terms. So if we take what can change here? Well, the magnitude of A can change, the magnitude of B can change, and the angle between them could change. Okay, so if I start taking derivatives of those, it's not really easy to see that you're going to be able to prove the first line. It's not obvious. So, fallback, then, is to return to the Cartesian form of the dot product. So may I have a volunteer to recall for the class, the Cartesian form of the dot product. That is, if A and B are expressed in Cartesian components, then what is the dot product? Somebody other than Mr. Avery.
Thank you. I'm up to date.
Mr. Vestal.
AX, BX
Good.
plus AY, BY.
Yes, and in 3 dimensions.
Plus AZ, BZ.
Right. Okay. Now, if we have a vector A, remember it can be written in form in terms of going along the x direction and amount AX, going along the y direction and amount AZ, going along the z direction and amount AZ. What is the time derivative of A? If A is expressed in this form, well, I just look at the dot products of the components. Right? Why don't I have the dot products of the unit vectors, x hat, y hat, z hat? Why don't I have time derivatives of those? Why don't those? Ms. Shaven?
Because they're constant.
They're constant. We've chosen Cartesian unit systems so that it doesn't move, doesn't rotate, they don't change, directions remain fixed, which makes things like derivatives easy in the Cartesian coordinate system. Okay, so the time derivative of a vector looks like this. Okay, so now let's go back to the time derivative of A dot B, and let's do this in terms of the Cartesian form, AX BX plus AY BY plus AZ BZ. Okay, so what's the time derivative of AX BX? The product of two functions.
It's the first times the derivative of the second.
Good.
Plus the second times the derivative of the first.
Okay, so I'm going to write it on 2 separate lines here. There's the derivative of the first times the second, and then the first times the derivative of the second.
Oh, so you about to product the whole thing out.
Do that with each one. We get 6 terms, right? 2 lines. First line involving A dots, second line involving B dots. Okay, now can you see the A dot X is the component of the time derivative, it's the X component of the time derivative of A, isn't it? This term, and this term. Those are the components of dA dt. So that first line is the derivative of A with respect to time dotted into B, this whole first line here. Right? And then the second line is going to be A times A dotted into the derivative of B with respect to T. Okay, which was what we were supposed to prove.
Oh, so you're just using Cartesian forms to verify that.
Correct.
Okay.
Now notice that this dot product doesn't depend on Cartesian form to be defined, God bless. I don't need the Cartesian form in order to do this, to do all of this, but nonetheless it's simple, it's easy, so I can pick any Cartesian form, doesn't matter what it is, any Cartesian unit system, and decompose the vectors in terms of those Cartesian components and then demonstrate that this is true. But now this is true independent of Cartesian components, right? Because I can write this down as a general expression that does not involve any particular Cartesian components. The time derivative of the dot product can be written like that, independent of any Cartesian coordinate system. Okay, now we're going to use that here in class, but I wanted to point out here you're going to do the same thing for the cross product in your homework, and so I'm giving you a hint as to how to go about doing it. Remember the form of the cross product in Cartesian components. Work it out from that. It's a little more complicated. The cross product is messier, but if you're organized about it, you'll be able to demonstrate that second line there holds. Okay, so now having done that, let's use a special case. We said that the time derivative of A dot B is going to be the time derivative of A dot B plus A times dotted into the time derivative of B. Now let's try, what if we take the time derivative of A with itself? Any vector with itself. So B is A here, right? So dA dt dotted into A plus A times dA dt. Now can we simplify this?
That's just 2 times.
Yes, sir. Mr. Flanagan says it's just twice this. Why is that? Pardon?
Dot product with itself equals 1.
No. That would be true for unit vectors, but A is not a unit vector.
Because when you're adding 2 of the same thing, that's the same as multiplying by 2.
Yeah, but why are they the same?
Wow, what's the same?
These two terms here. This term and this term, why are those the same?
Commutative.
They're commutative, right? The dot product is commutative. When you do the cross product, it isn't commutative. So you can no longer do that with the cross product. Okay. So that's equal to 2A times dA dt. So let's suppose that we look at, the time derivative of R dot R. So that's going to be 2 times R times the time derivative of R with respect to t, and what is that? That's dr dt. What's dr dt? Mr. Averett, what's that?
Dr dt is
Mr. Covington, what's the derivative of position with respect to time?
Velocity.
Thank you.
oh, that's
The velocity.
You're saying R is just the radius?
R, if R is position.
Okay, that makes more sense.
If R is position,
I was thinking it's like radius or something. That's you had me tripped.
then the derivative of R with respect to time is velocity. Okay, now, what if R, the magnitude of R, is constant? So suppose R is a constant. However it moves, its distance from the origin doesn't change. So it's moving on a circle. So what is the time derivative then? What is R dot R in terms of the length? You almost had it. It's not 1 because this is some vector. So R dot R is not 1, but it's R squared. It's the square root of the length, right? If R without the vector over it means the length of the vector, then if we take the dot product of a vector with itself, we get the square of its length.
Oh, really? Okay.
And if the length is constant, let's take the time derivative of this. What is the time derivative of the square of the length? If it's constant. 0. And this is the time derivative of R dot R, which is 2R dot V, we just proved. So what does that say about the position vector and the velocity vector?
The velocity vector is 0.
Is that?
If the position is fixed.
Yeah, okay, so if the velocity vector would be 0 only if the position were fixed. But if it's moving around on a circle, it's not fixed. It doesn't have 0 velocity. But what does it say? The dot product of R with V is 0. R dot V is 0. What does that imply?
Direction doesn't matter.
Yeah, either R is 0, or V is 0, or third possibility.
They're both 0.
What would that be?
They're
What is it? What happens about two vectors whose dot product is 0?
They're perpendicular.
Perpendicular. V is perpendicular to R. So it might be that R is not 0 and the velocity is not 0. V must be perpendicular to R. So let's draw the motion here. We have this body which is moving around on the circle, but it could be going back and forth, right? Could be doing all kinds of stuff, but it just stays on the circle. So let's draw the position vector at some time, and how about the velocity vector? We know now it must be perpendicular. So the velocity is either that way or this way, right? Velocity is either to clockwise or counterclockwise, but it must be perpendicular to R. So that's circular motion, right? All we did was to say the distance doesn't change, and we found out the velocity has to be perpendicular to the radius. But that makes sense, right? Its velocity is always tangent to the circle. It's moving around. Let's take an example of a pendulum. A pendulum is held in place by a rod of fixed length. So we have a bob that swings back and forth like that. Its velocity is changing, isn't it? Speed is changing. Speed at the top of the swing is 0, has maximum swing velocity speed right at the bottom. Goes to 0 again, comes back. But what can we say at all times? If this is the position vector, the velocity vector is either that way or that way. It's perpendicular to R in the pendulum. Regardless of what's happening in the pendulum at that moment, the velocity dotted into R is always 0. Okay, so that's circular motion. The pendulum is an example of circular motion. A car going around a circular racetrack, that's an example of circular motion. It's not uniform, necessarily. Certainly not in the case of the pendulum. Now I said that something makes it uniform. What was the uniform circular motion? What was that? The second aspect of uniform circular motion. First was that the distance from the origin is fixed, but the second, the speed is fixed, right? Velocity changes because it's changing direction. As it goes around the circle, the velocity changes because it's changing direction, but the speed is the same all the way around. So uniform circular motion was constant R and constant speed. Okay, so let's try that thing. Constant speed, how do we write that in terms of the velocity vector? If we have the velocity vector, how do we get the speed?
Absolute value.
Divide by the unit vector.
That would give us the direction. You can't, don't divide by vectors, remember. You might think to divide by distance, by the magnitude, but don't divide by the directions.
So we're trying to find the velocity vector?
I want to find the speed. If I know the velocity vector, how do I get the speed?
The absolute value.
Absolute value, or in terms of parallel to what we just did, magnitude. But what did we do when we calculated the distance from the origin? I had the position vector, and how did I calculate its length?
Dot product.
Take the dot product. The dot product of the velocity vector with itself gives us the square of the speed. Can you see it coming? If the speed is constant, what's the derivative of the square of the speed with respect to time?
0.
So this is the derivative of v dot v. What is dv dt?
Acceleration.
So what have we learned about the velocity and the acceleration?
They're going to be perpendicular.
Yeah. A is perpendicular to v. This is uniform circular motion, right? We've got that condition, uniform circular motion. All right, let's draw these vectors. Here's R, and let's suppose it's going counterclockwise. So this is V. And V is perpendicular to R. Let's think about how that works. We'll take R at two different times, R and then R at a later time, r of t plus delta t, and we'll take the difference. So the difference then is going to be almost tangent to the circle. If we make delta t smaller and smaller, it becomes tangent to the circle. And so this would be the difference between those two would be the velocity times delta t. So you can see why if the delta t is made really small, the velocity is going to be perpendicular to the position. Now, and so let's do the same thing for the velocity vector. Now the velocity is changing, only in direction. So we have it, here's velocity at one time, and then at a later time we have the velocity t plus delta t, and we're looking for the difference between those two vectors. The difference between those two vectors is a vector that's pointed inward. That makes the acceleration opposite to the displacement, the position vector. It's oriented back towards the center. Not outward, but inward. In order to keep the velocity moving, you see the velocity is turning towards the inside. In order to keep, if you're steering a car, you're turning around a circular track, you're steering towards the inside. You're steering it inward, not outward. So you need to have, the velocity is going to be continually steered inward. It needs something to change it inward. So that change inward is the acceleration. The acceleration is inward. Back along the radius vector. Interesting. Okay. So uniform circular motion, those two facts. Velocity is perpendicular to the radius, and the acceleration is perpendicular to the velocity, in fact, back along the radius vector in the opposite direction. Okay. So now we're ready to give it a try. I'm going to set up a Cartesian coordinate system. I'm going to set up a Cartesian coordinate system, x hat and y hat. And I have a body that's going to move on a circle, uniform circular motion. Means that the velocity is a constant and the distance from the origin is a constant. That's a pretty eggish looking circle, but I'll try and smooth it out a little bit. There we go. Okay. So let's suppose we know the angle, theta. And the distance, we're also given the distance because that remains constant. So what are the coordinates x and y? I want to know the position vector now as a function of theta. So in other words, what are the x and y components? Because if I have x and y, I can write the position vector. So we have a little triangle here. So Mr. Fanning, how about we give this one a try? I have a triangle here, x and y components. So what is the x component? If I know r and theta, what is x?
R minus root of y.
You're taking the square root of r squared minus y squared. Yes, that would be, if you're trying to form that. I'm looking for the trig relation between r and theta and x. Mr. Disharoon, what is the x-coordinate of that triangle? What's the x part of that triangle there? The red triangle I've drawn. R cos theta. Good, thank you. And how about the y component? That's the sine. And in fact, I could factor out r length, God bless, as the common factor there. And so I can identify here pretty easily that this piece is r hat, right? R times r hat. So I've written r hat in terms of the angle. Okay, so far so good. Okay. Now, in uniform circular motion, how does that angle theta change with time? What is theta of t? It's uniform circular motion. Imagine that thing going around the circle. kind of
So what do you want it?
So could you be like?
terms of time.
So could it be like WT?
Yeah.
Right, omega
So,
t.
You know that the velocity is constant, so you could say V equals. Oh yeah, that works.
You could set. You could say it's certainly linear in time. You could say it's. I have an offset theta 0, which I could choose to be 0. That's where what the angle is when the clock starts. When the clock starts at 0. So let's choose that angle to be 0 when the clock starts, and if we do that, then we can get rid of the theta 0, and we could choose that to be 0. So theta is just increasing linearly in time. Right? Does that make sense? That angle just keeps increasing in time linearly. So let's rewrite the position vector now. We've got the position vector as a function of time. R of t is going to be r times x hat cos omega t plus y hat sine omega t. And this omega is going to be the omega, the velocity vector, the angular velocity, the magnitude of the angular velocity that we talked about before. It's coming here, so you'll see that. So that's omega. All right, we've got the position vector. Let's calculate the velocity. Okay, so remember this piece was r hat here, and this was the direction vector, r hat. Okay, so we have two pieces here. Miss Mall, what is the derivative of the distance with respect to time? Just remember, this is uniform circular motion.
Just the derivative of distance with respect to time, is that just velocity? Or
Uh,
distance with respect to time?
So the derivative of the position vector with respect to time is velocity.
Right.
But what is the derivative of the distance? And remember that we have, this thing is moving around on the circle, so how does the distance change in time? The distance from the center of the circle.
The distance from the center of the circle doesn't change. It's
Right,
constant.
exactly. So how about the derivative of that with respect to time?
It's going to be zero.
Good. Okay. So now we just need dr hat dt. Let's look at the derivative with respect to time of this thing inside here, cos omega t plus y hat sine omega t. Okay, the derivative of x hat. Ms. Watson, how about the derivative of x hat?
Is it just going to be 1?
No. Does x hat change with time?
No.
Right. So what is the
It'll be
derivative?
0?
It'll be 0. So the derivative of x hat is 0. So all we have here is the derivative of the cosine with respect to time. And the same for y hat. Okay, and now we're starting to see why we need the trig functions again. We reviewed them for simple harmonic oscillator, and they're coming back here for uniform circular motion. Okay. How about the derivative? I'm going to ask Ms. Watson again here. The derivative of cosine omega t with respect to t.
It's going to be negative omega sine of omega t.
Good. And?
It's going to be omega cosine of
Good.
omega t.
Very good. Okay, so the velocity now is going, and notice there's a common factor of omega.
Oh, you can't change X.
I'm going to pull that out. There's the velocity vector. And back here, the position vector. Okay, so let's check a couple of things now that we've made some progress here. How about r dot r? Remember, r is r times x hat cos omega t plus y hat sine omega t. So we take the dot product of that with itself. Okay, so we get r squared, and then we get 4 terms. X hat dot x hat dot y hat dot x hat dot y hat. How many of those terms are not 0? 2. So we're left with cosine squared omega t, which is the x hat dot x hat term. And sine squared omega t, which comes from the y hat dot y hat piece. And what is the sum of cos squared plus sine squared, Mr. Jackson?
1.
Yes, very good. Okay, so this is what we wanted. The position vector, the length of the position vector is r squared. That's good. How about v dot v? Let's check that. That was omega v. I'm sorry, omega r times minus x hat sine omega t plus y hat cos omega t. And then we have dotted into itself. All right, we get 4 terms again. 2 vanish because they're x hat dot y hat, and they're perpendicular to each other. And we get sine omega t squared, but it's a negative sine omega t, but that's squared, right? Plus cos squared omega t. What is that inside the square brackets, Mr. Tremblay?
Still 1.
It's still 1. This is the speed, the square of the speed. So the speed of the body in uniform circular motion is r omega, right? That confirms what we saw earlier. All right, lastly, let's take the dot product of r and v. We want to see that this is perpendicular. Dotted into r omega minus x hat sine omega t plus y hat cos omega t. All right, that should come out to be 0. So let's look at the x hat and x hat components. So this is minus cos omega t sine omega t. And the product of the y components. Do those cancel? Yeah, they're opposite, equal and opposite to each other. So this is 0. Good deal. All right, next step is to compute the acceleration. We have the velocity vector. Let's compute the acceleration. So that was d by dt of the velocity vector was r omega times minus x hat sine omega t plus y hat cos omega t. And the derivative of r is what? 0. And Ms. Swanson, how about the derivative of omega?
0.
Yes, ma'am. Why?
Because it's a constant.
It's a constant. The thing is just moving uniformly. The angular velocity, so-called, is the same. The speed is the fixed all the way around. Omega doesn't change. So those are just constant factors that come out. And now I need to take the derivative of sine omega t. So please do that for me, Ms. Swanson.
That would be negative cosine, negative w cosine, or omega,
Sure.
sorry, cosine
There you go.
omega t
Uh-huh.
plus, or minus.
Good.
The omega sine omega t.
With a y hat in there.
Sorry.
Yep. Okay, common factor of omega. Let's pull it out. Negative omega. Minus x hat cos omega t minus y. Oops, I pulled out negative already. There we go. Sine omega t. Okay, does anything look familiar?
It looks like SMH, SHM.
Pardon?
It looks like
SHO?
harmonic motion.
There is some resemblance to the simple harmonic oscillator because uniform circular motion looks like simple harmonic motion combined in 2 different directions, out of phase with each other. Right? That's what he demonstrates that, in fact, in the chapter on simple harmonic oscillator, I think, or maybe it's coming in uniform circular motion. I can't remember where he does that. But uniform circular motion is like a combination of simple harmonic oscillator in the x direction and in the y direction, just out of phase with each other. If you consider the x and y components, they're out of phase. Okay, but I'm looking for something here in the mathematics. What is this combination in square bracket? What does that look like? We've seen it before.
Acceleration.
What, that last one?
Yes, this last part here. Anybody recognize that?
Oh, that part.
Yep, that part.
That was r hat.
Yes, sir. R hat. So the acceleration is minus omega squared r hat. Didn't we say that it was going to be opposite to the direction of r?
Oh, okay.
So r is r hat. V is r omega times something perpendicular to r hat. I'm going to give it a name here. We'll work on this. You don't understand why I'm calling it theta hat, but it's perpendicular. It's in the direction it's perpendicular to r hat. We're about to do polar coordinates, so you'll understand what I'm doing here. The magnitude of A is omega squared r. The magnitude of V is omega r. And the magnitude of r, of course, is just r. Okay, so the acceleration, this is interesting to notice. The acceleration of a body in uniform circular motion is omega squared r.
Oh, so what's in the negative? Or just
The magnitude.
Okay.
So the negative sign here gives you the direction, it's inward.
So
But the magnitude, which is directed inward, is omega squared r. So what does that mean? In order to keep it moving in uniform circular motion, that's the acceleration I have to apply to it by some external force. Has to give you that. Let's write that in terms of velocity. We have omega here. Let's eliminate, if we eliminate the omega, the acceleration is v squared over r. If we eliminate omega. The acceleration of a body moving with speed v around a circle of radius r, uniform circular motion, is going to be v squared over r. Regardless of what force provides that, whether it's a rope or friction in the tires or whatever, something has to provide that. But whatever it is, that's the acceleration on the body that results from some force being applied that keeps it moving in a circle. V squared over r. So we're going to use that a lot. This is a very commonly occurring relation. The acceleration of a body in uniform circular motion is v squared over r. If v is the velocity, or in terms of omega, the angular velocity, the acceleration and velocity are related to r and omega that way. Okay. So if I'm driving around a circular track with some speed, then what provides, and the track is not inclined, it's flat. What provides the force that keeps me moving around the circle, keeps me moving in uniform circular motion rather than just moving straight off tangent?
You're in a car?
Yeah, in a car.
The fact that you're turning the wheel?
Yeah.
Inward acceleration.
Yeah, I'm looking for the force that provides the acceleration is the friction of the tires.
Oh,
If the tires are bald or you're doing this on ice, you're not turning in a circle, right? You're going to go straight. So it's only the friction in the tires that will keep you moving. So the tires have to direct a force inward, and that force has to be match this mv squared over r. It has to be of that magnitude in order to keep you moving in a circle. So the force of friction, in this case kinetic friction, has to equal that. I'm sorry, static friction. In case of it's static friction because the tires are moving. The tires are rolling without slipping. So pardon me. Static friction is what's providing this inward force to keep you moving around the track. If I double the speed, what happens to the force that's necessary? Quadruples. You've got to have 4 times the friction, which is why it's easier to go out of control by driving too fast, right? How about if I double the radius? Actually, it goes down. Force of friction goes down by a factor of 2.